So this video is going to be talking about something called a differential and also linear approximations. We've done some equations of tangent lines already at a point for some function f of x. So let's just kind of formalize that a little bit. Just remind you what that is. The equation of a tangent line is y minus y1 is equal to m times x minus x1. That's the equation of any line. But for a tangent line, we know a little bit more information. First off, y1 is your function evaluated at that point. So it'd be y minus f of a. Your slope for a tangent line is the derivative evaluated at a. And then your x1 value is a. We can simplify this a little bit just to get y by itself. We're going to add f of a to both sides. So f of a plus f prime of a times x minus a. Now that's the tangent line. Near the point A, that tangent line will be approximately the same as the function value. So f of x is approximately equal to f of a plus f prime of a times x minus a. And even though your function probably isn't a line, isn't linear, you can actually think about it being approximated by this line. So we can actually do what we call linearization of f at that point, which means we can actually find a function, we'll call it L of x, which is actually equal to the f of a plus f prime of a times x minus a. So what we're basically saying is if you zoom in close enough and far enough into a function, it'll look like a line, and this is the equation of that line. And we can use this to approximate functions, value functions, close to that point A. Now, in this day and age, we don't really need to do this as much, but if you have a table of values for your function, then this is very, very useful. We're going to look at a problem that's analytic, but you can do this with table of values. I just want to show you the process here. So let's say we have a function f of the cube root of x. So f of x equals the cube root of x. We want to find the linearization of f at x equals negative 8. I'm going to use to approximate f of negative 7.9 and f of negative 8.1. So we want to find the linearization of that. So the first thing we need to do is our f of x is the cube root of x, which is x to the 1/3. And then we need the derivative. So let's find the derivative of that. That would be 1/3 x to the negative 2/3. And then we're going to evaluate this at negative 8 because our a value is negative 8. So we're going to have negative 8 to the 1/3. So that's negative 2 because negative 2 cubed is negative 8. Then we're going to do f prime of negative 8. It'll be 1/3 negative 8 to the 2/3. That's a little bit more work to try to figure out, but we can do it without too much trouble. I'm going to go ahead and get rid of the negative exponent. So that's negative 8 to the 2/3. And the cube root of negative 8 is negative 2, because we just said it was. So we know that part. And then you're going to square it. So you're going to get 4. So 1/3 times 4, or 1/12. Now we can do the linearization. The linearization will be f of negative 8 plus f prime of negative 8 times x minus a negative 8. So f of negative 8 was negative 2. F prime of negative 8 we just found to be 1/12. And then we have x plus 8. So that's negative 2 plus 1/12 x plus 8/12, which would be 2/3. So negative 2 is negative 6/3 plus 2/3 is negative 4/3. So we have 1/12 minus 4/3, 1/12 x minus 4/3. And there's our linearization. And we can now use that to approximate different values. So like I wanted to approximate f of negative 7.9 and f of negative 8.1. So we want to find the approximation of f of negative 7.9, and that would be approximately equal to the linearization at negative 7.9. So that'd be 1/12 times negative 7.9 minus 4/3. So We can do this without a calculator. You can actually figure out what this is without a calculator. You have the knowledge of doing that. I'm going to use my calculator only because of time, but you can do this just fine without a calculator. And we find out that that's approximately equal to negative 1.992, let's say. So we now have that this is approximately equal to negative 1.992. We can also do f of negative 8.1. Again, that would be the linearization of negative 8.1, which is equal to 1/12 times negative 8.1 minus 4/3. Again, we could do this without a calculator. This was very, very useful before we had calculators. But again, this will be very useful if you happen to have a table of values and you don't know what that value is. So we have negative 8.1 divided by 12 minus 4/3. And that's approximately negative 2.008. These are approximately close to what it is. Remember, negative 8 is negative 2. So f of negative 8 is negative 2. So these should be close to negative 2, and they are. Both of them were very close to negative 2. And so we have that. Now, the farther away you get from an x value that you're using to approximate from a, so if you want an x, like if I did negative 7 instead of negative 7.9, we're really far away from negative 2. Not 7, negative 8. Really far away from negative 8. So we get a worse approximation. But that's okay. We can still go ahead and do these approximations and get certain values. So they still give us an idea. You get over an estimate if f is concave down. And the reason that is that if you're concave down, then your linear line goes on above the graph and above the function value. So you get an overestimate, and you get an underestimate if you're concave up. Because again, if you're concave up, then your linearization is below the graph, and you get slightly less values. There are some places where we use these approximations. We actually have an application in physics that uses this a lot. We have a function, let's say f of x equals sine of x. I'd like to find the linearization at 0. So again, first thing I got to do is find f prime. So let's find f prime of x. And the derivative of sine is cosine. Then we need to know what f of 0 is. That would be the sine of 0. And we need to know what f prime of 0 is. That would be the cosine of 0. Well, the cosine of 0 is 1, and the sine of 0 is 0. So now we can get the linearization. The linearization would be f of 0 plus f prime of 0 times x minus 0. So that will get me 0 plus 1 times x minus 0, or times x. So that tells me, remember, the function is approximately equal to that. So the function, by the way, the linearization says we get x. And that tells me the sine of x is approximately x when x is near 0. Now, where we use this in physics is in pendulums. If I take a pendulum and I let it go back and forth, my angle is really, really small, and I'm really close to 0. So I can actually use this approximation to make my values with dealing with pendulums much, much smaller to deal with, and much less complicated to deal with, because I can use the sine of x as approximately equal to x when I go to do my pendulum work. This is only when we have really small angles. If you had a pendulum that was going wacky all over the place, then you can't use this approximation. But usually when pendulums are going, we have very small angles we're dealing with. And we use this approximation all the time when we're doing that. All right, so now the next concept I want to talk about is something called differentials. So we have a y is some function of x, and it's a differentiable function. The differential dx is the independent variable to the differential dy. In other words, we can rewrite our derivative as dy. So I'm actually going to do it this way just to show you where this comes from. So I'm going to tell you that we've got dy dx usually, and that's the same as f prime of x. Well, we can actually think of taking these dy and dx as separated apart, and we can actually make dy solve for dy, and we get f prime times dx. And so this is very, very useful for doing some work on differentials and working with these values. So what I want to look at is why we can do this and what this actually means. So let's look at a graph of this. So we're going to draw a graph here and show you kind of what this is talking about. And so we have, and I'm just going to draw it in the first quadrant. There's no reason it has to be in the first quadrant. You can draw it anywhere you want. I don't care where you actually draw it. So let's go ahead and draw a function. I'm going to draw a concave down. It could be concave up. Again, this doesn't matter. And I'm going to take some point. I'm going to pick some point right here. And I'm going to say that this is some point x. And I'm going to draw the tangent line to this point. So there's the tangent line to this point. And what I have with this is I can come over a distance, delta x, a certain distance over. I'm going to call that distance delta x. And we come over here to some point right here called x plus delta x. Well, the really cool thing is delta x and dx are the same thing. So they actually are the exact same value. They mean the exact same thing. And we come over here to this point. Where we use this is we're going to come up here. The distance from here to here, and we can think about drawing over here, drawing kind of a little triangle in here. This is my y value. And up here, I have another y value. So this distance here is delta y. If I kept going up to this tangent line approximation up to here, and I get this y value for here, then I have this distance here, which is dy. So we can actually see that delta y, which is again equal to your f of x plus delta x minus f of x, that's what delta y is equal to. dy is approximately equal to that. So delta y is approximately equal to dy. And that's where we can get into these differentials and deal with this and what we can use them for. So let's do an example with differentials. Show you what this is talking about. So where we use these a lot is to estimate errors. So we have a circle, a radius of a circular disc. It's given by 24 centimeters with a maximum error in measurement of 0.2 centimeters. So remember, when we measure, you aren't ever perfect with your measurement because you have some error in that. And this is what this is talking about, is you have some error in your measurement. You can only measure as good as your measuring device can do. So if you measure 24 centimeters and you're only measuring every 0.2 centimeters, then I can only say I'm 24 centimeters. I could be 24.1 centimeters or 23.9 centimeters. I can only get within that 0.2 distance. What we want to do is we want to use differentials to estimate the maximum error in the calculated area of the disk. So we'll start with that, and then we'll worry about the next part. So part A, I want to use that. So first off, I want to find delta A. That's what I'm looking for. I want to know the error in the calculated area. That's what I'm looking for. That's what delta A is equal to, is that error. This is a circular disk, so we have area is pi r squared. So what we're looking for is we're going to look for what is dy. And to do that, we first need to know what A prime is. Well, A prime is 2 pi r. And I hope you notice that this is the circumference of a circle. So the derivative of area is circumference. It's kind of a cool piece. So we have that. And so we have this derivative. And now we can find, using differentials, we can approximate delta A. Delta A is approximately equal to dA. And from what we just came up with this is that this is equal to the derivative at A times dr. Remember, dr is delta r. And we just said delta r was 0.2 centimeters. So we now can do all this. We can find out what this is. This is going to be 2 pi. My radius, going back up here, look real fast, my radius was 24 centimeters. So my radius was 24 centimeters. So I'm going to have 24 centimeters. And then times dr, that was 0.2 centimeters. I'm sorry, 0.02 centimeters. So all I got to do is multiply all this together, and that tells me what my error is, my maximum error. So multiplying 2 times 24 times 0.02, I can do that all without a calculator. That's 9.6 pi centimeters squared. And so that's what my error is. If you want to find out what this is approximately, you can find out what pi is and use your calculator to approximate that, but that is what it is exactly. Well, approximately still, because it's still approximate. Part B would like us to do the relative error. Well, the relative error is always equal to the change in the error area over the area itself. So that's going to be approximately equal to this delta A over A. So again, delta A was 2 pi r dr, and A was pi r squared. So first off, you're going to notice the pi's cancel. So we get 2, one of the r's cancel, so you get 2 dr over r. So that's going to be 2 times 0.02 centimeters, that's delta r. Over top of r was 24 centimeters. And we can find out what that is approximately if you want to. So approximately that would be 0.0167. So that's how you find relative error. If you want to have the percent error, the percent error is just the percentage of that. So it's going to be approximately equal to 1.67%. And that's how we can deal with differentials.